now Intel will be selling you devices made of carbon. I honestly don't care. As long as it poses an interesting question, that's fine by me. And so, just to summarize, and I think this is also something one can learn, you can really get a lot from doing this experiment theory collaboration, because you have a really beautiful experiments, and it's really hard to pinpoint the physics just by doing the experimenters. You can get from detailed understanding, you can get design principles. Of course, the semiconductor people know this for 60 years, but in molecular electronics it's extremely important because you have an infinite amount of molecules. So trying to screen all of them like they do in pharmaceuticals, it's just, you know, an impossible task. You really need design principles. And the final word on molecular electronics is still whether or not it will become a technology, who knows? I don't know. I think it will to some extent, but I don't know. And with this, let me acknowledge the people who actually did the work in Bing-Shen Shu's group, Hunan, who is actually now a postdoc in the Weizmann Institute in Israel, Kuhn, who is looking for a postdoc, probably will start in Michigan, Bin and Joe, who are postdocs in this Bing-Shen, and my student Elinor, who did most of the calculations in DNA transport. In fact, all of them. I didn't do anything. And let me just thank you for your attention.
Question, comments?
Can you get microwave radiation from the negative differential resistance in your system?
You could,
But
theoretically.
how to detect that? Because the power will be extremely small.
Yes, yes. So that's one of the reasons to go to molecular electronics is that the power is so small. So the idea of really using negative differential resistance devices here is not really to mimic microwave sources, but really to use them as switches. Mm-hmm. Right? And the idea is that when you have a molecular device, it's very hard to gate it. Mm-hmm. Right? Because how do you come so close to a thing which is so tiny? Mm-hmm. So it's very hard to gate these devices. A few groups can, but it's extremely hard. So really what you want to do is kind of make a transistor which relies on these two voltages, right? You're at 0.8 voltages, you get some current, you go to 0.82 electron volts, and there's no current at all. Or the current drops down 6 orders of magnitude. So this was the idea behind negative differential resistance devices. It's not really to mimic other devices.
Yes, because you said the molecule is rather plain, simple. So that's not special about the molecule. Is that the difficulty comes from the electronic contact or the measuring system?
Here? Mm-hmm. So, okay. There's nothing special, even after what I said, there's nothing special about this molecule. This term, this exciton magnet, is in every molecule. Only that in order to see it, you need to access transport optically. If you do just a regular charge measurement, regular IV curve, you will never see this. It just does not come up. Not really. Because it just does not affect transport so much. Because you're typically off resonance. You need to go to large voltages, it's going to be hard to see. So there's still nothing special about this molecule, besides the fact that, I mean, what is special here is really the experimental setup, that he has this planar bridge and he can shine light from it. Now this molecule, presumably, you would see this effect in any molecule, right? Any symmetric molecule. If the molecule is not symmetric, then this effect would be shadowed by the fact that you have a symmetry. Then you're opening this other channel for conductivity. But for symmetric molecules, every symmetric molecules will do that. They are actually now trying to do that with the other molecules. Unfortunately, the student who did this graduated, and the student who is working on it has only been there for a few months. And these experiments are extremely challenging. So it will take a while, but they're going to do it.
In the first part, how come the negative differential resistance is only observed in the positive bias? And in the second part, you say the transport is coherent,
Yeah.
but if it is coherent, you should observe the quantum resistance, right?
Okay, let me first answer the first question. It's easy like this. Let's go to the data. Where was it? Yeah, there it is. Yes, so well, it shows me that you should see it here. Wait a second. Duplicate. Okay. So the first question was, yeah, I'm not sure what we want. Let's try this. So the question is why is it not symmetric? Yes, keep changing, please. Okay. So the question is why is this not symmetric? And the simple answer is that I don't know. There is some asymmetry embedded in this junction. Now, there should be some asymmetry always, because the molecules, when they couple to the electrodes, they're not behaving themselves, right? They just sit all over the place. So if a molecule is sitting like this, but there is a bump here in the electrodes, I mean, there's some surface roughness to the electrodes. So depending on where the molecule sits and where, and the angles and so forth, that will depend, that will determine these things. Now, mind you, these are specific curves. This is not the average. On average, half of these show up here. Okay, so on average, this system is molecular, but this is just two specific curves. Yeah, I didn't show well, they didn't show, what they do in the paper, they show these samples, and then they flip them all to be on the same side just to make it look nice. But in this system, on average, it's on the negative side. Yeah, you cannot control it uphill, which kind of makes it not a very useful device, granted, but interesting in terms of science. Okay, so there is no real and the other question
About coherent transport.
Yes. No, there's no reason for you to expect unit conductance. Coherent transport does not imply quantum conductance, because the channel is just not good enough.
The junction transmission is too low.
Exactly. So the way it works is that you have a transmission function, and at resonance, you would have the quantum conductance, right? So if there were a way to gate this molecule in order to put it in conductance, you would hit the quantum of conductance. And indeed, in the group of Herr-Vandersen, they do it quite regularly, and they always see the unit, the quantum conductance, in small molecules, when they can gate them. But when you're off resonance, you are off resonance, and you're very far from the conductance.
Yeah, that comes to the third part of your talk. When you shine a light to the molecule, you hit the molecule and the electron to the resonance mode. Right?
Yeah.
And then you should observe quantum conductance.
It's not the same resonance. So, okay, I again have to go back. So when I say resonance in terms of transmission, yeah, sorry about this. I'm going back to one of the first slides. So, okay, when I talk about resonance in transmission, I really mean this point. Or better again, I mean a situation where the molecular level is right in line with the Fermi levels. And this will give you something which looks like this. And this is, if you want, the density of states. So resonance means that at zero bias, you are at the maximum density of states. And this implies that the molecular orbital sits right at the Fermi level. This never happens. Molecules and metals live on different points in the energy landscape. There is always a gap, and it's typically anything between 1 and 3, 5 electron volts. So you are typically off resonance in this situation. When I said optical resonance, what I meant is that the photon energy is exactly the one that matches the difference between this energy and this energy. So you're in optical resonance, so to speak, which has nothing to do with the transport resonance. These are subtleties of the profession. But the thing is that you should not expect the quantum unit of conductance in you know, as is molecules without gating them or somehow.
Any other question, comments? Larry.
So in the last part of your talk, can I just understand what you are trying to do is to compare the conductance of a molecule in ground state and in excited state? Can I just naively think?
Well, what I'm trying to, well, first of all, what I'm trying to do is to figure out what's going on in experiments. You're asking what is the motivation for this? Well, at this point in the life of single molecule electronics, the motivation is really to demonstrate capabilities. Now, this is hard to do. I mean, these experiments are very hard to accomplish by. So even if there's no use to having such a device, then it's still fun. But then again, you can definitely think of about optical switches, right? You have a system which you can turn it on and off, right? Think about having a current and, you know, maintaining the system at very low voltages, say, I don't know, 0.1 volt.
So what I'm trying to say is that by nature, this is the conductance difference between the ground state molecule and the molecule and excited state.
Yeah. Oh, so what I'm trying to understand is why is there a difference between?
But should we expect there must be a difference?
Why? That depends on what you know about molecules. So when you tell this to chemists, and they say, yeah, there's always.
The population is now in the ground state, so all the transmission.
Well, but let's say you have a Coulomb. Let's go to the language of solid state physics, and you make these two-dimensional DEG, and you make a Coulomb, a quantum dot out of it. And if the quantum dot is large, where the Coulomb interaction is small, then you wouldn't care, right? You pump electrons one by one, and the different levels, they do not feel each other because there's no dependence of the energies on the number of electrons. So so in that case, there will be no interesting physics going on. The fact that molecules behave more like small quantum dots is exactly what you say. And this is why what I'm saying here is just pinpointing the difference between a transport of a ground state and excited state molecule. Right? Of course there is a difference in the conductance, I just want to know why is there a difference and can I control it and optimize it. Definitely, this is, so when you tell this to chemists, which have been doing, for example, optical spectroscopy in the gas phase, they will say, there's nothing not trivial about this exciton binding energy. Nevertheless, it has not been considered in the literature for some reason.
Well, maybe one possible experiment is just to embed a junction in the matrix of different dielectric constant. So just
that is harder said than done. Oh, easier said than done. So, easier said than done. It's very, so coupling this molecule to anything but gold is an extremely hard thing to do because they don't like each other. You need to glue them together. So you can couple them to gold, you can couple them to silver, sometimes you can couple them to other things, but coupling a single molecule into a dielectric material, or even worse, having a dielectric environment that's a controlled dielectric environment, that's very, very hard to do. So the easiest thing to do is just to change the molecule and hope you get something.
Right, I think we better stop here. Thanks, Yoni.
Oh, more.
He'll be around for some time, so if you want to